A few years ago, Target managed to identify which of their shoppers were pregnant, long before those customers had publicly announced the news to anyone. The company didn't have access to private medical records, nor were they breaking any privacy laws to make these predictions. Instead, they relied on statistical models to connect seemingly innocuous everyday purchases, like unscented lotion or specific vitamins, to uncover major life events. As this presentation slide points out, Target wasn't collecting private data, but their creative linking of information allowed them to make private revelations with a high degree of accuracy. Even when data gathering is legal, uncovering these hidden patterns can feel deeply invasive, creating a massive trust risk between a company and the public. The engine behind these predictions is big data, massive datasets defined by their volume, velocity, variety, veracity, and the ultimate goal of extracting meaningful value. This diagram shows the black box. Data enters as input, passes through an opaque center, and exits as a prediction. We see data in and results out, but the intermediate step remains a mystery. Even developers struggle to explain. This chart breaks down the different branches of artificial intelligence. While traditional analysis follows human-readable logic, the inner segments here, neural networks and deep learning, operate through mathematical abstraction. Inside the network, the sigmoid function compresses raw data into usable probabilities, mapping inputs between 0 and 1. The algorithm then checks its work using a mean-squared error function, calculating the difference between its prediction and reality to refine accuracy. Based on those errors, the AI rapidly adjusts millions of internal connections, finding microscopic data patterns that no human brain could ever perceive. This relentless self-correction is exactly what makes the AI so accurate, but it also makes its logical path impossible for a human to trace. Developers don't just hope the black box is right. The machine must prove its accuracy on unseen data through a technique called cross-validation. In 5-fold cross-validation, the system splits data into 5 segments, training on 4 parts and testing on the hidden 5th. It repeats this cycle 5 times, rotating the hidden piece, then averages the results to ensure it hasn't just memorized the training set. This process allows developers to mathematically guarantee the system works, yet they still cannot explain the specific logic the machine used to arrive at the right answer. These algorithms are not neutral. Their invisible connections reflect human choices, thresholds for inclusion, and any biases present in the historical data. When an opaque black box makes crucial determinations, like loan approvals or hiring decisions, it can quietly consolidate existing societal prejudices. This lack of transparency destroys trust, leaving consumers feeling vulnerable to and controlled by devices they don't understand. Prioritizing predictive accuracy over transparency creates a societal risk where no one can be held truly accountable for a machine's mistakes. To address this, researchers are developing Explainable AI, or XAI. XAI is a suite of methods designed to inspect and unpack hidden models, making their internal logic understandable to human operators. This graph illustrates the rapid acceleration of technology. As we reach the point where AI intersects with IoT infrastructure and quantum computing, transparency becomes a necessity. The long-term viability of AI depends on a shift in focus, moving from machines that are simply accurate to machines